Hello and welcome back to STEM Online Academy. My name is Jason Masterakos. I'm not going to go into that much introductions. So what we're looking at uh, is specifically this concept. Okay, a lot of students fail. Okay, when it comes to the applications of you know calculus, derivatives, integrals, uh, all of that jazz, right? Because not because they are not smart and do not do it. It's because you're memorizing formulas, right? And procedures instead of not using, asking the important questions. Okay. All right. Pretty much things like accumulation, area accumulation, rates of change, instantaneous rate of change, right? Or sometimes even both. Okay. So it's very important to ask those important questions, right? If you ask, pretty much it comes down to this, if I'm going to be honest, right? If you ask really good questions, right, and you then think about those questions in detail, you it will help in the learning process. Okay. So here are some thought-provoking questions we're going to talk about in this video that I think you'll find interesting. All right. One of them is okay, when should you think of rate of change, okay, instead of just the formula? Okay, that's going to be question number one. Question number two is when should you think of accumulation in terms of, instead of area, right? Even though both have to do with the same thing, right? Um, but I'm giving one analogy in terms of another. Okay. Number three, when or actually why does optimization problems feel hard even when the derivatives are easy, right? So why are optimization questions hard when derivatives are easy? Okay, so that's one of the other questions. Another question is why does uh, physics problems, okay, become obvious once you identify what is being conserved? Okay, what is being conserved, and what is it? And finally, how do you know whether, right? How do you know whether an integral, sorry, how do you know whether a problem wants a derivative, an integral, or both? The last question is very important and very intuitive. Okay, so let's get right to it. I'm going to answer these questions. Okay. So, when should you think of rates of change instead of a formula? When should you think of rates of change instead of a formula? All right, so let's go to over here, the second screen, the whiteboard right next to me. Okay. If you look at the whiteboard here, okay. All right. So again, whiteboard. So when to use derivatives versus when to use integrals. So let's talk about the rates of change a little. I'm going to give an actual geometric example, right? A visual representation. Okay. And this is going to be really handy for hard calculus problems because quite often optimization problems will be under the category of hard calculus problems. Okay, and don't worry, I want to actually interject something very important about myself. At one point, I had trouble with um, problems of this nature, but not in university, but from grade 7 to 9, I had trouble with uh, word problems, problem solving questions. It wasn't because I couldn't do it, it's because I was focusing on the algorithmic problems, right? The problems that you can do again and again and again, and they don't change as much. They're pretty much the same boring old question. Problem is you're given most of these questions from your teachers, and it re-evaluates your assumption, restates your belief, thinking if you're doing well on a problem, oh wait, I must be doing well in math in general because I'm doing well in all of these problems for homework. The problem is the problems for homework are not the ones that show up on tests and exams. Okay, so that's really important. All right. So my point is, 7 to 9, I was having trouble. Right. Until two teachers showed me that the way to do mathematics is actually by using a particular type of system. Okay. And that system, well, you have to create a system for yourself. Everyone is different. Okay. Now, the system that I used, right? They didn't give me the exact system, but they told me that I have to use a certain problem solving technique. Okay. System that I like to use, right? And I've talked about this before. If for those of you who haven't seen my videos, you may want to look at the other ones. But I talk about my technique, and the technique is the following. Okay. It's the systems technique. We may go down here. And I'll just put it down here so the systems. So 1 second. We'll go right here. Just give me a second. Here it is, a systems technique. There's a systems technique. And this works for from the easiest to the hardest problems. It won't solve the problem like automatically and give you the result. No system will do that. And if I was to claim that, that would be bad of me. Okay. But what it can do is going to open up your intuition uh, to become much stronger. Okay. All right. So here's the system that I use. Okay, so step one, we're going to use visualization. So visualize the phenomena. Right? Quite often, I'm sure a lot of you have gone through this. Okay, where you had to deal. You couldn't just use a formula, plug it in, and then solve it. Quite often, the problem is much more complicated. It requires you to maybe use some visual spatial technique. So a lot of these analytic calculus problems or calculus problems, you're going to have to be able to do that. And physics problems too, right? So step one, visualize. Okay. Visualize either geometrically or physically, right? Visualize the problem. Okay. So either with a simulation or you may have to draw a graph or do some geometry. Okay. So visualize. Next step, you want to be able to model the phenomenon. Okay. What I mean by that is you come up, you list what you have and don't have from the visualization, right? And either you list what you have or don't have, or you assign appropriate variables and quantities to the visual diagram to make it make more sense. Okay. All right. So from the visualization to the model, right? Then from the model, okay, from the model, from the model, you want to be able to execute. Now, the execution phase, I want to explain. The execution phase is the phase in which you're able to mathematically map from the visualization to model to the execution. You're coming up with a formula from the visualization point of view from step one. Okay. And you're plugging and shutting the algebra. Okay. Then from there, the final step is to verify the results. The left-hand side is equal to the right-hand side of your equation. We don't have I'm not doing a specific problem in this video, but I'm just giving you an example. I think you understand what verify means, right? Okay. So left-hand side and right-hand side should make sense. Okay, so verify what is going on. Okay, so verify. Verify. Okay. That is what we have for systems technique. This technique got me through high school and it delivered phenomenal results in university. So much so I got a 3.85 GPA in university with a double major math and physics. Okay. So yes, this technique I can attest to is very, very powerful. Right. Okay. More about that when we get right when I get to the next part here. Okay. So let's get back to it. Okay. So that's my systems technique that I quite often use. But I wanted to look at when to use integration, when to use differentiation, right? So let's look at rate of change first, okay? All right, so when it comes to rates of change, right? You can see here, right? I give you an example of rate of change, right? You have some curve there, okay? So there's some red curve, like you see in the diagram right next to me. And then you can see that there's some sort of a tangent line. Remember, a tangent line hits the curve at exactly 1 point, okay? And not just that, what is a tangent line? Tangent line is conceptually the instantaneous rate of change from the first derivative of the original function. The original function is that red curve. So wherever that red curve is, that red curve will represent y equals f of x. Okay, we will take its first derivative, right? Right, and then after from the first derivative, right, we get some function of x, and that will be the tangent line. Well, not quite. It gives us the slope as the function of x, right? Then we have to get um, the instantaneous rate of change, right? Is by determining, right, getting the coordinate, one coordinate that hits the tangent line exactly once at x equals some number, okay? And we plug x equals that number into the first derivative of the function that we had, and that will give us the slope of the tangent line, okay? Only the slope, right? And then from the slope of the tangent line, right? We have the slope of the tangent line, m. We have the coordinate x. Hopefully, you have the coordinate y, right? Then we use the point slope form and we find the entire equation of the tangent line. So the entire equation of the tangent line is that red line that intersects that point exactly. Okay? So right here, if you can see that. Okay, I zoomed in. A little green dot there. That's the exact coordinate x comma y. That hits exactly 1 point of the tangent line. Okay. Right, so this is right. This is exactly right a geometric representation of what I'm talking about. Okay. All right. And a visual representation of rates of change. Okay. Now let's get into the physical part of it. Okay. So number two, right? Number two is again rates of change, but it also has to do with area accumulation. So area accumulation and rates of change. Okay. So what am I talking about here? Here, what I'm talking about, okay, is the following. All right. Let me just move this over, and we're going to make it maybe a bit bigger if you can see that. Okay. So area accumulation. Okay. And rates of change. So here you can see a physical application, an application to physics, right? Where we have distance versus time, and we have two cars, right? One car going in one direction, the other car going to the other direction. Okay. You can see from the picture, right, on the graph, it's distance versus time, right? Again, exactly the same graph as above. We're taking some red curve, that's our function of x, or a function of time, sorry, in this case. Time is the independent variable because it's not changing, because it's changing. So that's the red curve, okay? Now, we want to, let's say, for instance, measure the instantaneous velocity, for instance. Right? Want to measure instantaneous velocity, you want to measure its average velocity. Average velocity is its regular rates of change, right? No derivative is needed there, by the way. Okay, so I want to close that misconception that there's no first derivative for average velocity. It's just the rate of change formula, right? In this case, uh, the average velocity, okay, is minus 11.5 kilometers per hour. That's the example that they're giving. Okay. Now, the instantaneous rate of change geometrically can be represented by that purple line, the purple dotted line there, right? Okay. Purple dotted line should be the instantaneous rate of change because it hits exactly at one point. Okay. And since it hits exactly at one point, we have to calculate the instantaneous rate of change. We'd have to take its first derivative. Okay. So purple line should be, yeah, purple line should be, if I can see that properly, the instantaneous rate of change. The green line, however, is to represent, the green line represents the average velocity. Okay, why is that? I know the green line represents the average velocity because it's the average rate of change. An average rate of change is represented by a secant line, where instantaneous rate of change is represented by a tangent line. Tangent lines only hit exactly one point on any curve, whether it's a curve, cusp, or circle, it only hits one point. Okay, and the secant line uh, hits two or more points on the curve. In this case, the red curve. You can see that green line here. We zoom in even more. Okay, I hope you can see it. Really trying to zoom in. There's the green line hits that green point there, but then the line is also hitting other points on the red curve. So that's not a tangent line. That's a secant line. So that's the average velocity at minus 11 kilometers per hour. Okay. All right. So I hope that's making sense in terms of what I am doing here, right? Conceptually. Okay. All right. So this is an interesting application that we have here. Now let me talk about the area accumulation. Okay, the area accumulation. What do I mean by that? It's nothing to do with slopes, with tangent lines or secant lines. Area accumulation has to do with the area below the curve, right? So from the left, the most left part of the red curve to the most right part where the curve ends, try and imagine green bars under, or any type of rectangular bar graph underneath that curve, and it goes all the way upwards. Okay. All right. So that would be the area under the curve. Okay. All right. Now, why is that of significance to this situation? This is a distance time graph. Yeah, I mentioned instantaneous velocity. Yeah, I mentioned the average velocity values from the lines and everything like that. But the distance time graph is calculated by getting the area underneath the velocity time graph. Okay, so be careful. I only showed you a distance time graph. If we were to compare it with the velocity time graph, okay, the velocity time graph. So you would start velocity. Yeah, let's say you started with a velocity time graph for a reason. You want to get to distance time, you'd have to calculate the area under the velocity time graph, and that gives you the distance time graph. So the velocity time graph wouldn't have been a red curve, it would have been something else, okay? Maybe you can figure it out conceptually. Try to figure out visually what the velocity time graph is, and then you can please put it in the chat. I always like to communicate with you. Put in the chat once I've uploaded this video, and I can conceptually fix any misconceptions you have if you have trouble visualizing what the velocity time graph is. But if you know some calculus, it makes it easier. Or you can use physical intuition to figure out what the velocity time graph. Okay. But yeah, you'll just be calculating the area under the curve of velocity time, and that gives you that red curve for the distance time. Okay. All right. I have a few other things I want to talk about here. Let me see. I have them written down. Just one second. Okay. Let's see. Oh yes. Why do optimization problems feel hard even when the derivative is easy? That's a very uh, that's a very good question. Okay. So why are optimization problems hard when derivatives are easy? Derivatives are easy because you don't need a system's way of thinking. You just need to use algorithmic formula. Okay, so dy dx, for instance, for a derivative, and you use the appropriate dy dx depending on the type of function you have. Very straightforward. Anyone can do it. Okay. However, not everyone can do an optimization problem because the optimization problem requires you to set up and model the problem. See where the difficulty is? You have to set up and model the problem, then, well, I'd like to say visualize the problem, then model it, then you do um, the algorithmic part, which is the easier part, which is just plugging in the algebra. But the harder part with the optimization problems compared to derivatives is the fact that you have to set up the problem. Whereas derivative problems, it's already been set up and you just use a formula. Okay. So that's why optimization quite often is annoying, difficult, and creates problems for people. Okay. All right. So the other question. So why do physics problems become obvious once you identify what is conserved? This is another question I want to bring up. Okay. So why are these problems obvious once you identify what is conserved? Well, the reason for that is you need to know physically what is happening in the problem. Okay, right? So, for instance, I'm not saying that this problem per se has to do anything to do with conservation. It doesn't. Conservation of energy, mass, or angular momentum, or any of that. That's for another video, maybe. But my point is that here, since we're talking about the application of calculus to physics, right? So velocity, displacement, velocity, acceleration, right? You need to know back and forth what is happening. Okay, right. So I wouldn't use maybe the word conserved, but I would say is the interrelationship between displacement, velocity, and acceleration. Okay, how how they behave, what they mean, and how you go from one to the other, and how do you go backwards from one to another. Okay, when you understand that, then it becomes easier, right? You see how everything is working. Okay, so you have to be able to go back and forth when it comes to the physics applications. Okay, and then finally we have the question. Was it? I don't remember all the questions. I haven't written down. Where is it? How do you know whether a problem wants a derivative and integral or both? Okay, this is the most important question when it comes to a hard calculus problem or calculus-based physics problem, right? So how do you know when to use derivatives, integrals, or both? Anytime when you need, especially when it's an application problem, okay? All right, so I might write something down here, okay? So when you're going, so I'm going to write something. Let's see here. Going from, okay, when to know. Let's say when to use integrals, rules, versus derivatives. Derivatives. Okay. So number one, okay, when you're calculating anything to do with area, so when calculating, okay, so anytime when you're calculating anything to do with area, right, calculating anything to do thing to do with area, you're gonna have to integrate. Okay, so you're gonna integrate. Okay, make sure you understand that. It's very important. Anytime anything to do with areas, you're gonna integrate. Okay, because you're calculating the total accumulation under the curve, which is the summation of all the rectangles under the curve calculates the area. Okay, All right. So number two, when has to do with anything to do with, let's say, slopes or instantaneous rates. So I'm going to put number two here. Number two, when calculating anything to do with, let's say, slopes, with slopes, over here, with slopes slash uh, instantaneous rates of change, you need to differentiate. Okay, differentiate. Please remember that's very important. Okay, you're going to differentiate. Okay, it's so important to know this. All right, area you integrate, slopes, instantaneous rates of change, you will differentiate. Okay, all right. So that is it for today's video. I hope you enjoyed it, and I hope you got something from the video. That's the point of the channel, is to hopefully help you guys conceptually understand hard calculus concepts and problems, as well as physics problems as well. Okay. Okay, so that's it for today's video. I promised you guys that I'd be doing twice, what was it? Let's see, twice a week. Yeah, twice a week, Tuesdays and Sundays preferably. I may incorporate another day, but I probably not. Because YouTube's a lot of work. So twice a week for now. Let's see what else. Uh, let me think. Oh yes, before I get going, all right, about my technique for um, hard calculus problems and calculus-based physics problems and anything else, right? My technique that I use, my semantic model technique, right here, okay? I made a short PDF, which is actually for free, that you can find in the link below of this YouTube video on how to use this technique and when to spot patterns of where this technique will help the most. Okay, that will be a free PDF in the description below, as well as all of my other resources and services will be there as well. If this technique, you read the PDF, but you're still having, and you've applied it, I want you to apply it first to actual problems and see if there's benefits, if it's helping you. Okay, if not, and or you're not understanding it, um, you may want to reach out for another resource, right? My new book, Axioms, which goes through uh, some of the, you know, logical pitfalls a lot of people have when it comes to calculus. Okay, it's always good to have a prerequisite resource that can help you. It will be available in the link below. There'll be one link that has all this stuff. Okay, and or if you're looking for tutoring specifically will be online face to face, where I will be explaining how to solve these problems. Maybe you need more attention as opposed to a resource, right? There's a difference. Uh, Getting more attention can be beneficial. You can reach out to me in the link below, or preferably just in the chat. The chat helps as well. Okay. Again, thanks for watching the video. I appreciate it. So to all the subscribers, anyone new, like and subscribe, please. It helps the channel, it helps the algorithm, and it helps me in general. So please like and subscribe. That would help a lot. And yes, next week we'll go into more interesting concepts as well that will help you for those hard midterms and exam questions, as well as for independent learners who enjoy mathematics and advanced science. Thanks again, and have a great weekend. Bye bye.